Hello, I'm Richard Patterson and I'd like to welcome you to another science demonstration video presented by IPC Irwin and CPD Science. And in this Series 2 episode, we're going to return to electromagnetism and back to our Westminster Power Supply. So the Westminster Power Supply is a specialised unit and it will work with all the electromagnetism practicals that we're meeting in junior and senior high schools. And we recommend that students work in pairs and have one of these when they go through the electromagnetism practicals. So just to look at the front again, it's got a DC output of 1 volt and an AC output of 1 volt. Now for this experiment we'll be looking at the DC, but in later work with transformers you might want to be using the AC. So the Westminster unit will provide 12 amps at 1 volt, either DC or AC, which amounts to a power of 12 watts. So students need to be aware that wires may get warm and the unit itself may get warm, since there's no trip switch inside. Inside the secondary coil, there are very few turns of wire, which means we can short out either of these terminals AC without causing any harm to the unit. So we're going to investigate how the Westminster Power Supply can be used to look at the force on a current carrying conductor. And this will lead to Fleming's left-hand rule and the electric motor in a future video. So what we've got here is 2 copper conductors, and resting on them is a loose conductor there which can move back and forth freely on the wires. And we've connected the 2 ends of the copper holding wires to the 1 volt DC supply. Now all these components come from the Westminster electromagnetic kit. Now these kits have been around for about 40 years. They are available from major suppliers and they come in different shapes and sizes, but they all have the basic components in which you see here. Because we're using an old kit, we've got this wooden varnished frame here. You may need to improvise, or if your kit hasn't got one of those in, but it is essential for your students to succeed in this that there is a clamp holding these copper rails firmly, and that this moving conductor makes good contact with those copper wires. If there's any tarnishing on there, you might need a bit of emery cloth to clean it up. So we're talking for a class of 32 of 16 sets of this equipment, because it is quite small and intricate, and really if there's 3 students working with this, there'll be one hanger-on, a passenger, who won't really get involved. So if we're happy about that setup there, we now bring in this what we call a mild steel yoke, and it has these ferrite magnets placed on either end there. So you need to check that there is a strong uniform magnetic field between there, and you need to of course check that there is attraction between those 2 magnets and they're not repelling. So we've got a north and a south. And you can use a plotting compass. If you carefully bring the plotting compass into the yoke there, it will rotate and we can see which is where the north seeking pole is going to. There. Be careful with these compasses, of course, because they're quite easy. If you overdo it, they might flip from being north seeking poles to south seeking poles, because they're not particularly robust. But this one appears to be still working correctly. So we'll label the north and the south in a minute, but for the time being, just instruct the students via a worksheet or whatever method you use that they need to bring in the metal yoke so that it's just resting on the frame and not touching anything. Now at the minute, this particular yoke seems a little small, so I'll just put a little bit of packing underneath there. But whatever you do, make sure that the wire is free to move within the yoke. So we'll switch on and hopefully we'll see our result. So I hope you caught it there. The wire, the free wire moved in that direction there. So at this point, you want your students to start thinking about Fleming's left-hand rule, and you have to introduce them to holding their left hand with their thumb, first finger and second finger, what we say mutually at right angles. Now, the thumb has got an M in it, and that's used for motion, movement, which is the direction that the moving conductor was propelled, which is that way there. And we can add, if you need it, a M on the thumb, just to remind the students of that means. Now, the first finger is the direction of the magnetic field, so that will be down like so. And just behind, you can see that the second finger, the C in second stands for current, is pointing towards me. And if we look at the arrangement, indeed the current, conventional current, flows from positive to negative, so the red is coming in along there, and indeed the direction of the current in the free moving conductor is coming towards me. So Fleming's left-hand rule is applying to this demonstration, and the next step is to reverse the various magnetic fields and currents and see if the movement corresponds. So in terms of directions, the first thing we can change is the direction of the magnetic field. So we could just invert the yoke. So now the magnetic field is from north to south, as shown by my first finger there. The current is still towards me, as shown by my second finger, so the predicted motion should be that way. And there we are. So the last thing we can change direction will be the current. So on the supporting frame, I've changed the way the black and the red are connected. I reversed those. So the current is now, conventional current is coming out of here. It's going into the supporting wire, and now it's going down towards the camera and out through the black. I've changed the direction of the magnetic field to its original, and so if I'm holding my left hand there, my thumb is now showing the direction of motion again. The magnetic field is down and the current is coming out. So we'll just place that there and hope that it works. Okay, so that's all the combinations of Fleming's left-hand rule, and what we'll look at now is other factors we can change in this experiment. So further investigations with Fleming's left-hand rule and the motor effect involve changing the strength of the magnetic field and or the strength of the current. This is best done as a teacher demonstration. So what I've done here is I've connected a rheostat in series with a IPC Irwin 10 amp DC ammeter, and by careful adjustment we can observe qualitatively whether the push on the wire, the force on the wire is less or greater. So if we just try the magnets, I've doubled up the ferrite magnets there, and we'll put that in there. Taken the rheostat out of circuit, and yeah, judgment, that rod moved faster, and that's so it's accelerating, so that means a greater force. Let's see if we can change the current. Now with the rheostat, with this particular rheostat, I found that you really just need to take it into, bring it just a tiny little bit into circuit there, just a tiny fraction of the resistance coil to reduce the current. So if we try that again, we should be thinking that reduced current reduces the force. So again, that's really as it was before. If we just bring this into circuit a little more, so putting more resistance in, which means less current, slide that back. Can get quite warm, that, so just be careful. And now I switch on, there's a feeble push. It's not really overcoming the friction of the rails there. So again, that's a demonstration to show that if the current is reduced, the size of the force is reduced, and if the magnetic field is increased in value, the force is increased. So at junior to senior high school level, not getting into advanced work, that should be sufficient. Finally, we can have a look at these neodymium magnets as well, and again it's something for teacher to demonstrate. If you want to increase the current and magnetic field, you can bank these up on the metal yoke there, but do be careful with these. There's full safety instructions that they can actually pinch your skin if you get them jammed in between, because they're very, very, very powerful. So how do we explain to students where this force comes from? Well, in this graphic we use the term the catapult field, and we have two magnetic fields, a uniform field from the permanent magnets, and if you remember from the last video, we've got a concentric magnetic field around the conductor, and that's shown there in the two diagrams at the top of the graphic. Now when those two magnetic fields are brought together, this is the magnetic field known as the catapult. And if we think of the magnetic field lines below the conductor as being stretched elastics, just to help us try and understand it, if you can look at the stretched elastics, what they're going to do is try and push on the wire and move it upwards. So thank you for watching this video. All the instructions we've obtained from the Institute of Physics Spark website, where there's extensive teacher notes. And if you want to find out more about the Westminster Power Supply and the ammeter and Westminster kits, then again look on the IPC Irwin site and you can download all the instructions and find out more. In the next video we'll have a look at how this equipment can be used to actually make a working electric motor, and look at IPC Irwin loudspeakers which use this effect to make the sound and make them move.